Okay, this is a question a few of you had concerning the use of the ice bath as a reference junction, and I'm going to go over what I think is the explanation that makes most sense to me. And the question was, in this situation here, so we have our measuring thermocouple, T-type, measuring some temperature at the probe, and then we have a second thermocouple in series with it, and the junction of that thermocouple is in the ice bath. And then we have these two ends here that we're measuring the voltage across, and that's what we were doing in lab. And the question was, why is the measured voltage across these two nodes, why does that correspond to the temperature difference between these two junctions? Because that's what it's showing us. And so we are going to just kind of go through and I'm going to show how that works out if anyone's still confused. So remember that if we have a length of wire with a temperature difference that we maintain across it, this will create a voltage difference. So I'll call this end V hot and V cold, and the voltage difference between the hot and the cold side is going to be proportional to the temperature difference, and that relationship is related by the Seebeck coefficient. And so what we can do here is we can go around this loop, and that's what I'm going to do, and we're going to use the fact that the voltage difference from one end of each wire to the other, from node to node, the drop in voltage is going to be proportional to the temperature drop from junction to junction. So that's why I have these nodes labeled here and their respective voltages. So we'll just start at V1, and then I will just subtract out from this starting voltage whatever drops we would expect to see across each of these wires. So if we start with V1, and then our first wire we have copper, and we go from, we're assuming that the terminal block where we have this where we're measuring the voltage is going to be at some ambient temperature, and we don't know what that is, and that's important. So we're going to start here and go down. So we have the Seebeck coefficient of copper times ambient temperature minus the Seebeck coefficient of copper times the temperature at junction 1. So this should represent the voltage difference that we get going from here down to here across this copper wire. Okay, then let's subtract the next voltage drop. So we're going across the Constantine wire now. This is V2 to V4. Okay, so V2 we should be at the Seebeck coefficient of Constantine times the junction temperature at junction 1. And then we go down to V4, which should be the Seebeck coefficient of Constantine minus the junction temperature at junction 2. Okay, and then we'll go one more. We'll start down here, subtract one more voltage drop, and this time we're going across a copper wire again. So we have that temperature at junction 2, and then we come all the way back to this node here, V5, and we're assuming that these are plugged into the same piece of, or on an isothermal block. So we assume it's at the same temperature. We don't know what it is though, but that doesn't matter because we can see here from this expression. Okay, and so then when we get down to that value here, then we should be at V5, whatever that is. Once we start at V1 and we go all the way around the loop. And we can see that right away we have a minus minus here and just a minus here, so these Seebeck coefficient of copper times T ambient, those terms are going to cancel. And then we also can just move everything over here on the left side to the right side of the equation and then subtract V5 and rewrite this as V1 minus V5 equals, we should have a minus there. We should have that should be a TJ, and then we should have and that's it. So we rearrange, and then we know that V1 minus V5, well, that's just the voltage that we measured across our voltmeter. And then we can simplify this a little bit further, so we'll group together all the terms that have the copper Seebeck coefficient in front of it, and we'll say that this is going to be, let's keep this one at let's keep the minus out here, do TJ1 minus TJ2. So if I group these together, and then we will add to that this term, which also has a TJ1 minus TJ2. And then if I combine these again, then we can see right here, if I were to just combine these into, this would be like the combined Seebeck coefficient for a T-type thermocouple. We can see here that the measured voltage, again, what we were looking at up here, that measured voltage is directly related to the difference between junction 1 and junction 2, the temperatures of those junctions. So that's how we see that that works out. The other thing to note, so when you're actually reasoning through your lab reports and doing the discussion questions, the Seebeck coefficient is not a constant. The Seebeck coefficient is a function of temperature, and it changes with temperature. Now, it can be constant over a range of temperatures, or it can be predictable over a range of temperatures, and that's why different thermocouple types have different ranges of temperatures over which they're appropriate to use. So because this is not actually a constant, we can't just do this analytically, so that's why we can't just take the voltages that you measured in your experiments and just plug in whatever the Seebeck coefficient is and then work out what the ambient temperature that you measured was, because this is not a constant. So when the table that you have in your lab manual was developed with all the voltages corresponding to different temperatures, what they did was, or what I'm assuming they did was they, have another bath here that they're heating up, and you stick a RTD in here, and you get some, reading of temperature that's really accurate. And again, you keep this at ice bath, and they just constantly heat this up and keep getting accurate temperature measurements of whatever the water's at here at this junction, and they keep measuring the voltage. And so that's how they developed that table with all those voltages in it, because again, the Seebeck coefficient could be changing as a function of temperature, and all the values in the table were used with an ice bath reference junction. So that's chosen because it's convenient, because we know the temperature stays very constant. So had they taken this junction out and just had this set up here where you're just changing the temperature of this and measuring it and just taking this voltage here, that might not be accurate because the temperature, the ambient temperature, could be fluctuating. So to assume that it's some constant would not give you a good set of data. They could have chosen, boiling water to be the reference junction, so then if we were using that, we would have to compensate for that. But fortunately for this experiment, we were using the exact same reference temperature as the voltage values that were placed in the table. So that's how that works out. Hopefully you guys understand a little bit better why this measured voltage is giving us the difference between those two junctions.